Good afternoon, ladies and gentlemen. Welcome to the webinar, which is brought to you by SPACE, which is a Center of Excellence for HPC Astrophysical Applications. Today, we are going to address the ChaNGa code and the CHARM++ framework. Our agenda for today is that we will have a talk by our colleague, Robert Wissing, who is a postdoc working at the University of Oslo with publications in the field of numerical methods, magnetohydrodynamics, dynamo processes, galaxy formation, equation of state, and planetary impacts. He has developed the MHD module for the ChaNGa and gasoline codes and is currently involved in improving the scalability of the ChaNGa code. So this training is addressed to researchers interested in HPC and the challenges that astrophysics codes present when scaling towards exa-scale. We will discuss both the benefits and the difficulties of the ChaNGa code and the CHARM++ framework, and we will also discuss recent and future improvements of the code. So with this, I would like to ask Robert if he can take over the share and start his presentation.
Great. Yes. So thank you, everyone, for coming to this presentation. So yeah, as Karina said, I'm Robert Wissing, a postdoc of University of Oslo and a member of the SPACE. And today we're going to talk a bit about the ChaNGa code. So first, yeah, Karina already said, but the SPACE is a newly founded center of excellency that brings together expertise from scientists, code developers, software developers, and APC experts, which aims to prepare astrophysics applications for the exa-scale and beyond. And apart from the expertise provided by SPACE, we, of course, also have the ChaNGa collaboration, which is also known as the m-body shop. So me and Xijing Shen, both from the University of Oslo, is part of the m-body shop and also members of SPACE. But we're also collaborating very close with Tom Quinn, which is the head developer of ChaNGa, and Spencer Wallace, which is the postdoc of Tom Quinn and is doing a lot of development for the GPU porting of ChaNGa at the moment. And there's, of course, many more of m-body shop that we're collaborating with. So what is ChaNGa? So ChaNGa is an astrophysics code for cosmology and galaxy, star, and planet formation. So there are 5 major physics algorithms within ChaNGa that I'm going to talk a bit more about in this presentation. So the first is a tree-based gravity solver for solving gravity. The second is smooth particle magnetohydrodynamics, which is for the magnetohydrodynamics part. Then we have subgrid methods to model star formation, stellar and active galactic nuclei feedback. We also have prescriptions to model. So when we model a piece of the universe, we also have to take into account the interaction from the rest of the universe. And this is what cosmological boundaries do. And then we also include algorithms to model the radiative cooling that happens. And what is a bit unique about ChaNGa is that it, compared to other cosmological codes or astrophysics codes, is that it utilizes the CHARM++ runtime system to improve parallelism. And so just to talk a bit about the CHARM++, so there's basically 3 key features of the CHARM++ runtime system. So the first one is that it allows for an over-decomposition. So that means that you can have more work objects than there are processors. And then the runtime, so the CHARM++ runtime then can migrate these work objects around the different processors during runtime to improve load balancing. So the user doesn't have to do much, so the runtime takes care of it. And these work objects are called chars in the CHARM++ framework. And chars call entry methods to each other. And these are just basically, there are messages to each other. The message is returned immediately and returned void. So basically, the char that is requesting some information from another char just gets back an information. Okay, we got the message. We will get you the information eventually. So the thing is, so this message is queued on the the processor that the receiving SHAR is currently on. And this is how you can have, and this is called asynchronous, basically, messaging. And this is how you can have computation and communication be overlapped very effectively. Because after the requesting SHAR has sent the message and just received this message back immediately, he continues to work on other stuff. And this can be seen in this time profile. So here on the y-axis, you have what different processors are currently working on. So the red one is communication, yellow is local work, and the purple here is remote work. We don't have to care about the blue part right now. But you can see in the beginning, there's a lot of local work being done and a lot of communication being done by processors. And then eventually when the requested information comes back, then the remote computation can start. So that allows for very effective overlap. So some of the computational challenges that exist for cosmological codes like ChaNGa, I've just put down 4, which I could think of are the major ones. So the first one is that there is a very large spatial dynamic range. So for example, the distance to the closest star is about 1 parsec. Galaxy sizes are around 10 kiloparsecs, and distance between galaxies is 1 megaparsec. And maybe when we do a piece of the universe, right, we maybe model 25 to 100 megaparsecs. And that you can see here on the right, for example. Here we're modeling a piece of the universe. We're zooming in on a galaxy cluster, and then we're zooming in once more on a galaxy. So there's a huge dynamic range. And there's also a very large temporal range, right? Because the age of the universe, we want to model the whole age of the universe, 10 gigayears. And but the dynamic time within galaxies is less than 1 million years. So this requires a multi-time stepping scheme. And there's also different force ranges. So you have hydrodynamics, which is working just very locally, but then you have gravity, which works both locally and very long range, right? Or across the whole simulation, right? And there's also different particle species that we have to model dark matter, which only interacts with gravity, gas, which it has gravity, hydro, feedback, cooling, and stars, which has gravity and feedback. So one of the major physics, or the major physics element, which is the foundation of ChaNGa, is the gravity solver. And this is, okay, what happened now? Oh, there. So to solve like a very naive gravity implementation would be that each particle interacts directly with each other, right? So you calculate the gravitational interaction from each of the other particles in your simulation. And this is an n-squared complexity problem, right? So you have 4 bodies, there's 3 interactions each, which means that you have 12 interactions, right? And this grows to the square, basically. So a smarter way to do that is to use something like a barge hut approximation to actually build sort of bigger boxes that contain several particles. And what you create is sort of this tree structure where to calculate, where you can separate long range and short range forces, because the thing is the influence from distant particles can be combined together, right? You don't have to calculate the bodies of every particle in a box that is very far away from you, right? It's enough to just calculate the force from the center of mass. Well, in ChaNGa, we do a bit more fancy multifold expansion, but it's sort of the same thing. We do this to increase accuracy. And for you to sort of, and when you sort of, what we say is we do a tree walk to calculate if we need to go deeper within the tree to actually calculate the force or not. And this is based on a tolerance criterion. So you're still doing some direct particle interactions, but then you're also doing some cell particle interactions. And in ChaNGa, we also have a dual tree traversal. And this basically, in addition to the particle-particle and particle-cell interactions, it also adds cell-cell interactions to further reduce the complexity. And so the work objects that I talked a bit before, which are the sort of objects that are migrated between processors and load balanced, are tree pieces. And tree pieces basically consist out of three different partitions, or three different sorts, or what do you say, the nodes in a sense, right? So you have the local node, which are these yellow ones. So these exist within the tree piece alongside the boundary nodes. But the boundary nodes also exist on other tree pieces that go on, that has been cut differently. But the red ones here are remote pieces where you have to actually send a message to another shard and actually request that information. The bottom leaves are also buckets of particles and not actually individual particles. This is to make it a bit more computationally efficient. And yeah, so tree walks are basically separated into a local part and a remote part. And yeah, just to clarify, this is a tree piece in a sense. So how does the tree work progress? So you start the computation. You have several tree pieces. So this is an SMP node. That means that you have some processors that have shared memory. So they basically, they can share, what we do is actually we merge the tree pieces on an SMP node so that they all can do a local walk on the shared tree pieces. But you start communication, there is some local work that can be done on each tree piece. If any remote work is required, you try to request it. You look in your cache if it's present. If it's not, then you try to fetch it on a tree piece that is on another node. And then eventually you get the requested data, and then you can do the remote work. And then you end the computation. And this has worked very, very effectively for scaling ChaNGa. So here we can see a plot done on the blue waters in the US, where we see that the gravity part of ChaNGa, the full time step, but using just gravity, scales very, very effectively. So we can see up to 131,000, we have above 80% parallel efficiency. And this is a cosmological simulation with 2 billion particles. There is also a GPU offloading within ChaNGa. So there's two different ways right now how you can offload the gravity calculation to GPU. So the first one is to use this dual tree traversal, but the top part here, but there you create an interaction list. You send it to the GPU, you continue doing a new interaction list while the GPU works on that, and then this continues until, you do it. So you're doing a lot of the tree, you're doing basically the whole tree work on the CPU, but then just sending the computation to the GPU. However, quite recently, Liu 2019 basically ported the whole local tree work on the GPU. So now the whole tree work is done and the force computation is done on the GPU. The downside of this is only that we had to go back to doing a single tree walk compared to doing the dual tree traversal, because the single tree walk is much, much more parallel than the dual, even though it has higher complexity. And this has also worked very well for offloading the GPU to gravity. So first here on the left, you can see some scaling runs on the pistain. You can see here the GPU improvement, which is, I think it's like maybe even more. I think 3 or 4 times, or 4 times maybe better GPU scaling. And we have also scaled it to very high nodes on pistain. So showing quite well scaling there as well. Now I want to talk a bit about the hydrodynamics of ChaNGa. So specifically about the smoother particle hydrodynamics that we implement. So this is a Lagrangian particle method, and this describes the continuous fluid at any point by interpolating over particles, or rather interpolation points. So this is in contrast to sort of grid codes that you probably have seen previously, where you discretize the fluid into volume elements, but here you do it into mass particles in a sense. So it's a mass approach to discretization. And it uses a weighting function known as the smoothing kernel to smooth the fluid values so that you can get the fluid value at any point. And this smoothing kernels has compact support. So when the distance to a particle is above h, then it returns 0. So an important part of smooth particle dynamics is finding neighbors. But first I want to talk a bit about the advantages of SPH. So the first advantage of SPH is that resolution follows mass. So you can see here we have a galaxy. In the low density region, we have very few particles, which means that the resolution is bad. But in the high density, we have tons of particles, which means that the resolution is high. And for most cases, this is what we want, because the most interesting objects are usually the one with the higher densities. Second, there's no intrinsic dissipation within SPH, and it is completely Galilean invariant because it's from the Lagrangian. So that means that, so here we have the Kelvin-Helmholtz instability. So we have a high density fluid in the middle going to the right and a low density going to the left. Then this classical Kelvin-Helmholtz instability is formed. And this works very great for the grid when there's no sort of bulk velocity imposed on it. However, when you actually just put a constant velocity here to the grid, then you suddenly dissipate the instability. But SPH does not have this problem because it doesn't have advection errors. So it also remains Galilean invariant. Then there are also a lot of other advantages, like exact solution to the continuity equation, excellent conservation, very easy to track material evolution, and it couples directly with n-body codes. So the goal, right, in SPH from a computational sense is to find the nearest neighbors. And here we can once again use the tree build from before that we used in the gravity solver. So of course, the brute method would be to just calculate distance to each point, but this is an n-squared problem at least. But when we combine it with the tree build, we can reduce the search area. So here I'm just showing. So we have a query point here. We have a point which we want to get the closest neighbor to. We then go through the tree until we find the box which contains that query point. We look at the distance. We look at the distance for all the particles within this box. We keep the distance to the closest neighbor, and then look in which boundaries it intersects. Here we go down another sort of tree node, and there we find a new nearest neighbor, right? And we update this one. Now, of course, there's no more, and we actually no more boundary that it crosses, and we found the nearest neighbor. And this can very easily just be generalized into finding the k nearest neighbor. And k in SPH, or at least that we use, is around 64. So the remaining major physical algorithms, I'm just very quickly gonna mention them. So feedback has a similar computational challenge as SPH. So using k nearest neighbors to distribute feedback energy. And this involves, but the difference here is that it involves both star and gas particles instead of just gas particles. Radiative cooling, semi-implicit module. This means that you can have very large integration steps when the cooling time step is much less than the dynamical. And for cosmological boundaries, if you would just basically replicate the box, then it would have a very slow convergence. Thereby, we use Ewald summation to speed up the convergence. Just a bit about some different scientific applications. So cosmological volumes, which I've talked a bit before about. Here you simulate a patch of the universe and you capture large-scale structure and statistical properties. And this includes, of course, all major physics algorithms. However, the challenge is that you have limited resolution of individual galaxies and a very large dynamic range. So why do we want exa-scale? To, of course, increase the resolution needed to model all the galaxy formation physics with more realistic subgrid recipes. Zooming galaxies, similar to the cosmological, but here we add extra resolution to a small sort of region within the box. This is, of course, the challenge in this one is that you increasing the clustering of data even more, right? Because you're putting more resolution in a small region. And similar to the previous one, we want to reach a higher resolution to model more galaxy formation physics. Galaxy mergers, similar. The thing is that these galaxy mergers are usually done without cosmological boundaries, so they're usually isolated. And why do we want exa-scale for this one is to, at least for me, because I did implementation of magnetohydrodynamics, is to capture amplification of magnetic fields from turbulent dynamos and galactic scale dynamos. Another interesting is magnetized cloud collapse, which simulates the early stages of the star formation process. This one is interesting also because of the large span of scales. And it's also interesting because it only includes gas instead of using a lot of varied particle species. So it's an interesting computational challenge there also, because usually gas is much, much less than the other particle species. And now I'm going to talk a bit about the recent progress and the objectives within space that we have for the ChaNGa code. So the first one that you're going to see in the next slide is to improve the communication imbalance in very clustered data sets. The second is to improve the GPU version of the code and to start GPU offloading other modules than the gravity, which include the SPM-HD and the radiative cooling. And then we want to generate an extensive test suite and CI/CD for ChaNGa, and also port and scale on all European APC systems, and also explore improvements to vectorization. So for the first thing, so we have found from benchmarking now in the last year that we have a big communication imbalance in ChaNGa when we run very highly clustered merger simulations. And this leads, because in these merge simulations where we have all the physics, right, it leads to some tree pieces being requested much more than others. So a tree piece can have, I think 10 to 100 times more requests than others. And this leads to a significant delay in receiving messages. And you can see that in the scaling here, right? We scale up to 2000, but then it just plateaus or goes down even for 8000. And the optimization that we found for this is actually that we can do tree-piece replication. So we replicate the tree node information on multiple processors, which ensures that no single processor becomes overloaded with communication. And this has already, in this sort of alpha stage, seen to severely improve the performance when scaling. Another thing that we're doing here, you can see it says 16-com, 8-com. This means that 16-coms means that we're doubling the amount of communication threads that we're using to communicate between the different nodes. So ChaNGa uses SMP, which then has specific worker threads and specific communication threads. So for this case, increasing the amount of communication threads leads to better performance. And this is the single time step, and this is the gravity and SPH time. And we can see, as you can see, a very big improvement. Here is a bit of also just showing what are each of the processors doing. So here on the y-axis, you have each of the processors. There is, this is the whole time step. The different colored region is what is a processor doing right now. So in the beginning, you do the density for SPH, and then you do local gravity. But then, of course, during local gravity, there's also a lot of requests to start the remote gravity. But without tree replication, we can see that all of the threads are just basically waiting to get the requested information. However, with tree replication, this idle time reduces significantly, and the remote gravity can start much earlier. However, it can probably still be improved here, because what we would expect is actually complete overlap here. We also have started to do some GPU version improvements. So the first is a removal of the work request API, because an issue with this was that it limited us to one CUDA stream per processor element. However, we have found that, well, there's two. One is that the work request API is deprecated by ChaN++, so we need a new way. So what we did was that streams in GPU memory management is directly handled by the application now instead. And this allows us to basically control the number of CUDA streams. And this leads to also an improved behavior of the code and potential benefits also when we increase the number of tree pieces. We also added something to switch to do local tree work on CPU when we have very few active particles compared to doing it with on the GPU, because the GPU gives some overhead when you're doing it for, say that you have 10 million particles, but then you have a higher time step where you have 100 particles, and then doing it on the GPU for those 100 particles is not very effective. Yes, so in summary, three-piece replication improves scaling in highly clustered datasets. We have an improved GPU version now, and there's also now an extensive test suite available at this address. We have also ported the code, and we have shown that it scales for Carolina, Lumi, Leonardo of the GPU of the EuroAPC clusters. And there's also a public Git of ChaNGa if anyone is interested that you can go check out. And some future plans, we will further test the three-piece replication code and explore other improvements to communication. And also we have already started GPU offloading the radiative cooling, and we will also start offloading the SPM-HD. And also explore vectorization of SPM-HD model, because we have seen from benchmarks that the gravity seems to be much better vectorized than the SPM-HD module, which changes a bit of the optimization parameters that you want to use during your run. And yeah, thank you very much. That's my talk. Any questions?
Thank you, Robert, for the talk.
Thank you.
I hope there will be questions.
I do have a question.
Yes.
Please.
Yes, hi everyone. I'm Enrique from Barcelona.
Hi.
Hi. I would like to ask, just to make it clear to me, because you mentioned some of it at the beginning, if there is concurrency in the simulator when writing its output, which it seems like it, and
yes.
when generating its data in TIPSY files.
Yeah. When it's running, you mean when it writes to the output?
Yes.
Yes, then there is concurrency.
Okay.
Yeah. I didn't mention much about the outputting of data here. So there's, we actually have two different formats used. The main one is TIPSY,
yes.
But I think it's for very, very large data. We actually use another format which is called Enchilada. Because one of the issues with TIPSY format, or at least right now, is that it uses this for parallel writing, is that it uses MPI to do this. And when you're running on a lot of threads, it can sort of slow down the writing to this output. Because there's a lot of MPI threads trying to right to the
Okay, yeah.
Yeah. So, but the Enchilada does it better. So that uses actually also a ChaN++ library, which is called CK.io, which handles this in a bit of a different way. I'm not fully actually, because I haven't used Enchilada too much, but that is apparently a very effective way to parallel write, as I understand. Yeah.
Okay.
And this will be also implemented for Tipsy eventually, as I understand this new.
Thank you both for the question and the answer. Are there more?
Yeah, thanks, by the way.
So if there are no more questions, then thank you very much for the presentation, Robert. Thank you all for coming for today. And we hope to see you at our next sessions from space. There will be more coming in after the holiday break. So I wish you all enjoy a great vacation periods, and we hope to see you in autumn. Thank you very much.
Thank you, everyone, for coming.
Thank you. Bye.